Hey guys, so we're starting chapter 7. We're more than halfway through our content. Let's just get started. So, hopefully, you guys are following along on your actual notes and filling in exactly what I'm writing. Okay, so a statistic is a number that describes some characteristic of a sample. Okay, I've mentioned this in previous lessons, right? And a parameter describes a characteristic of a population. So the way I remember which one is which, okay, statistic starts with an S, sample starts with an S, parameter starts with a P, population starts with a P. That's how I remember which one's which. All right, so using the symbols we've already seen, okay, if it's a Greek letter like mu or theta, okay, that's for our population. If it has a hat, like X bar has a hat on top of it, or P hat literally has a hat on it, okay, then it's for sure going to be a statistic. Okay, now obviously not all of them, like standard deviation, this S does not have a hat, but the other option is a Greek letter. So the Greek letter is going to be the parameter for the population, and S is going to be the sample statistic. Okay, obviously P is not Greek, but the other option, P hat, has a hat. Okay, and hats are for stats. All right, so we can also look at it that way. Hats are for stats. All right, sometimes your book might talk about a thing called a point estimator. Okay, that is just your sample statistic. Okay, so the P hat, the X bar, whatever, if they talk about it and call it a point estimator, that is just also called your sample statistic. All right, so what we're going to do in these two examples, we're going to identify the population and the parameter and the sample and the statistic. So part A, the Gallup poll asked 515 randomly selected U.S. adults if they believe in ghosts. Of the respondents, 160 said yes. Okay, so it's a lot easier to start with the sample. Okay, my sample is going to be the 515. Okay. 515 randomly selected adults. Okay, to get the population from this, literally just change the number to the word all. So the population would be all U.S. adults. Okay, the statistic is whatever our sample is talking about. So our sample says 160 out of 515. Okay, so that's a proportion. So we're going to use P. All right, and if you look back over here for sample statistic P, it's actually going to be P hat. Okay, so P hat is going to be the proportion in the sample who believe in ghosts. The proportion in the sample who believe in ghosts. Now, if you just want to write the actual proportion, like if you just want to write 160 out of 515 to save space, that's fine, but the point is it's from the sample. Okay, the parameter is the same thing. It's the proportion who believe in ghosts, but for the whole population. And if we look back over here, all right, for the population, it would be just regular P, not P hat. So this is the proportion, let's say the proportion of all U.S. adults who believe in ghosts. And I don't have a fraction for that because we don't know the proportion of all adults who believe in ghosts. Okay. All right. During the winter months, the temperature outside the Starnes' cabin in Colorado can stay well below freezing for weeks at a time. To prevent the pipes from freezing, Mrs. Starnes sets the thermostat at 50 degrees. She wants to know how low the temperature actually gets in the cabin. A digital thermometer records the indoor temperature at 20 randomly chosen times during a given day. The minimum reading is 38 degrees. Okay, so again, I think the sample is easier. We have 20 randomly chosen times. So my sample is the 20 randomly chosen times. Okay, and what is it about this sample that we have? We have the minimum reading is 38 degrees. So there's no like symbol for that, right? Like over here, there's no symbol for minimum. None of these are for the minimum. Okay, so we're just going to write down the sample minimum temperature. Which was 38 degrees. All right, now again for the population, just change the number to the word all. So all times during the day. All times during the day. Okay, and the parameter would be, instead of the sample minimum, it's going to be the population minimum, or sometimes we call it the true minimum in the cabin. So the true min temp in the cabin that day. All right, and again, we don't know that number because they didn't give it to us. Usually we won't know the parameter unless they tell us. All right, so my thing about this chapter is you need to be clear whether you're talking about the population, okay, whether you're talking about a parameter or if you're talking about the sample, so the statistic. You need to be clear when we're dealing with Chapter 7 questions about which one we're working with in our problems. All right. So sampling variability, okay, basically what that is the fact that different samples are going to have different values. Okay, so right here we're going to say different values. So if I picked, like, let's say I picked 3 people from the class and I found the average GPA of those 3 people. If I pick a different 3 people, I'm going to get a different average GPA. Okay, so that's what sampling variability means, is that different samples get different results. Okay, now the sampling distribution of statistics is the distribution of values taken by statistics in all possible samples. Okay, it's supposed to be all possible samples. Now, you're going to see in a second that can get really large. Okay, the definition of a sampling distribution is for all possible samples. Okay, you get the statistics of every sample possible. I know I'm like repeating myself over and over, but like just trying to drive it home. It's every possible sample. Okay, so usually there's no way to do that by hand. Usually they will give you the sampling distribution because it's going to get ridiculous on how many possible samples there are. All right, so for example, John and Carol have 4 grown sons. Their heights are 71, 75, 72, and 68 inches. List all 6 possible samples of size 2. Okay, so I'm going to call this son A, B, C, and D. Okay, so my sample, I can have sons A and B. Okay, so 71 and 75. I can have sons A and C. 71 and 72. I like to go in a pattern, so I'm going to keep A and just make sure I get every combination with child A. So 71 and 68. Now I got all the combos with child A. Now I start with B. I already have B with A, so now I'm going to go BC. So that's 75, 72. And B with D, 75, 68. All right, now I already have C with A, got that right here. I already have C with B, got that right there. So the only one we're missing is C with D. So that would be 7268. So those are all 6 possible samples of size 2. Okay. Now, if I want to calculate the mean for each of these samples, okay, I'm just going to add the 2 heights, and since there's only 2 of them, divide by 2. So 71 plus 75 over 2, that's 73. 71 plus 72 over 2, that's 71 and a half. 71 plus 68 over 2, 69 and a half. 75, 72 over 2, that's 73 and a half. 75 and 68 over 2. And okay, so we have all of our sample averages, sample means. Okay, now just to we're gonna prove a point for something later on, let's get the sample ranges. Okay, so from 71 to 75, my range is 4. From 71 to 72, my range is 1. From 71 to 68, my range is 3. 75 to 72 is 3. This will be 75 minus 68 is 7. And 72 minus 68 is 4. Okay, so we are going to go and plot these on the number lines. So the first number line will be X bar. This will be the sample mean height. And this next one will just be sample range. There's no really letter for range. Okay, so my mean needs to go between 69 to 74. So that's not a 9. 69, 70, 71, 72, 73, 74. All right, so we have 69 and a half. We have, well, let's go in order. All right, so we have 73, 71 and a half, 69 and a half, 73 and a half, 71 and a half again, and 70. Oh, where am I? Okay, now for my ranges. All right, I need to make sure that I just have from 1 to 7, so I'll just make sure. So 1, 2. Okay, so I got 4, 1, 3, 3, 7, 4. Okay, so this is what a sampling distribution would be. You get every possible sample. So we got every possible sample of size 2. We found some statistic for them. So we found the sample mean for every possible sample. We found the sample range for every possible sample. And the sampling distribution is that graph we made at the end. Okay. So next question. To determine how much homework time students will get in class, Mrs. Lin has a student select a simple random sample of 20 chips from a large bag. The number of red chips in the simple random sample determines the number of minutes in class student gets to work on homework. Mrs. Lin claims that there's 200 chips in the bag and 100 of them are red. When Jenna selects a random sample of 20 chips from the bag without looking, she got 7 red chips. Does this provide convincing evidence that less than half of the chips in the bag are red? Okay. So first, why do we think it's less than half? Okay. We think it's less than half because our sample proportion, our p hat, is 7 out of 20, which is not half. All right, that's 0.35. Okay. Okay, it's less than the half that Mrs. Lin claims. So what are some possibilities of why Jenna got less than half. Okay, there's two options. One, I don't know, maybe just Jenna is terrible at selecting chips in the bag. Like she just got bad luck. Okay. Okay, so Jenna just got a bad grab, right? Like Mrs. Lynn is telling the truth. There is 50% that are red. Okay, and since this is I'm talking about the population of all 200 chips, this is going to be P, not P hat. Okay. Another phrase for this, like she just got a bad grab. Okay, that is sampling variability. Remember that from earlier? Okay, so some people just get a bad grab and they won't have, the 50-50 we're supposed to have. Some get a good grab and get more than 50% red. That's fine. All right, so this is one reason. The next reason could totally be Mrs. Lynn is lying. Maybe that's the other reason. All right, so Mrs. Lynn is lying. And P is less than 50. So no wonder Jenna got less than 50% in her sample. Okay, so the idea that what we're going to do in the coming chapters is testing whether or not, based on our sample, whether the claim is true, right? Like whether or not getting 7 out of 20 is low enough that Mrs. Lynn must be lying, or whether that's like, no, that happens. That's the idea of this whole chapter. All right, so we use technology to simulate choosing 500 simple random samples of size 20 from a population of 200 chips. So basically, we just did 500 of Jenna's grabs. Okay. So the dot plot shows P hat, the sample proportion of red chips for each of the 500 samples. There's one dot on top of 0.8. What does that mean? Okay, that means in one simulation of 20 chips, there was 16. Okay. In one simulation of 20 chips. All right. P hat was 16 out of 20. So that's crazy. Right? Like that's a way higher than the 50% we had. It's actually 80%. Oh, sorry, that's not A, that's C. All right. D, would it be surprising to get a sample proportion of 7 out of 20 or smaller in a simple random sample of size 20 when P is 0.5? Okay, so I'm going to look here. Here's 0.35 right there. Basically, is that super duper rare, right? Getting 7 out of 20 or smaller. Or is it like, no, that happens. Okay, and the idea is, no, like there's quite a few of them at 0.35 and lower. Okay, so no, there were many simulated results or simulated samples. That had P hat values. Let's do this for easiness. So had P hat less than or equal to 0.35. Okay. So based on our previous answer, is there convincing evidence that basically Miss Lynn is a liar and less than half of the chips are red? So since it's not surprising, like 0.35 or 7 out of 20 could happen by chance alone, we don't have evidence that Miss Lynn is a liar. Okay. Since P hat less than or equal to 0.35 isn't surprising, we don't have evidence that less than half of the chips are red. All right, so one more time, this is the idea that's going on. This is from the population, right? Mrs. Lynn said it was 50-50. Cool. So we get one sample. So this is one sample. We get our p hat, our sample proportion, and that dot goes like here. We get a different sample. We get its p hat. That dot goes right here. And we do that for, technically it should be every possible sample, like we had in the definition. A sampling distribution is for all possible samples of size 20 in this case. But sometimes, like, if you think about it, there's going to be, like, if you do the whole NCR thing, it's going to have a lot of ways to pick 20 chips out of 100. Okay, so instead, in this case, they just did a simulation of a lot of samples, so they got 500. Okay, but this is the idea. They did 500 different samples. So 1, 2, 3, 500 of them. Got all those sample proportions from each simulated sample and then put them in a graph. So that is what a sampling distribution is. All the possible samples, or a lot of samples, and their statistics in a graph. Okay, I just said that. All right. So a statistic used to estimate a parameter is an unbiased estimator. If the mean of its sampling distribution is equal to the value of the parameter being estimated. Okay, so like if we took all possible samples of 20 chips and calculated the p hats for everything and then found the average of all of those, you would get exactly what the p is supposed to be, what the population parameter is supposed to be. Okay, so in the sampling heights example, we created the sampling distribution of the sample ranges for samples of size 2 from the population of John and Carol's 4 sons. Is the sample range an unbiased estimator? Okay, so if you remember, so we had the numbers, if you just go and look at the number line we had before, the numbers were 1, 3, 3, 4, 4, and 7. So if I find the average of these numbers, okay, there's 6 of them, I get 3.67. But that's not what my actual range is. The actual range, okay, or sometimes they call it the true range, is biggest number, 75, minus the smallest number, 68. That's just 7. Excuse me. So the fact that these numbers are not the same, okay, this is not unbiased. All right, there's only one sample that'll get you the actual range, and that's if you happen to get the sample of the highest and the lowest. Every other sample is not going to get you the actual range, or even close to it, or even higher than it, rather. So there's no way the average of all those sample ranges are going to be the actual range. Okay. Now, what I will tell you is that p hat is always unbiased. All right, and the same thing with x bar. This is always unbiased. Okay. For example, if I chose to do the averages of, where are they? If I chose to do the averages of all of these, okay, if I got the average of all of these, it would be the same as the average of the original 4 heights. Okay, you're welcome to check it out, but sample means x bar, always unbiased. P hat, always unbiased. All right, what's so important about that? We want our samples to be a good representation of our populations. Okay, and a few more things. So larger samples tend to produce estimates that are closer to the population value. So like if I had samples of size 3 for those kids, okay, my X bars, my sample means, would be even closer to the true mean. Okay. What's the whole point of that? Like I want, like, see how this bullseye, this target, everything's really close to each other. I want it to be as close to the target. Okay. Larger samples are going to produce less variability. Okay. Like the fact that these are all spread out, larger samples are going to get those tighter together. Okay. So larger samples are going to produce less variability, so the dots will be closer together. And using an unbiased estimator, those dots are going to get closer to the middle. So like here, for example, they're very spread out. There's a high variability, but they're pretty dead, like averaged in on the center. Okay, so we want low variability. We want the dots to be close together, and we want it to be close to the bullseye. So we want unbiased estimators, and we want large sample sizes so that the sample statistics are close to each other. Okay, so that's this one. Oh, that's it. Wow, that was okay. I thought we had more. Anywho, so I have also given you guys a worksheet for 7.1. On the back is 7.2. You do not need to do that. Okay, but try your best to do the 7.1 worksheet at some point today or tomorrow. Okay, so some point on Tuesday or Wednesday, I'm going to post the solutions to it so you can double check your work. And we'll do a quick recap in class before we get started with 7.2. Okay? All right, if you guys have any questions, just try to, like, I don't know, put a sticky note on your notes. That way you can ask me in class on Thursday. And I'll see you then. Bye, guys.